My name is Mulong and I'm from Cornell University. The title of my presentation is Interrupt Attack on TE-Protected Robotic Vehicles. This is a work in progress. So why do we need TE or SGX for robotic vehicles? First, untrusted components in robotic system software and supply chain are very common. Second, trusted components can still be compromised. As a result, robotics vehicles' data and timestamp may be tampered by this. So we will introduce SGX or TE, but does it solve everything? First of all, the data and timestamp cannot be directly tampered by the systems. However, SGX enclave can still be interrupted by the system. We can use SGX step to do that. So the question now is, how interrupting SGX enclave affects robotic vehicles? To answer this question, in this work, we explore the usage of Intel SGX for robotic vehicles. First, we implement an SGX-based sensor timestamp module in ROS. Second, we performed interrupt attack on SGX using SGX step. Third, we studied the impact of SGX enclave interrupt on localization errors for robotic vehicles. Let's see how the timestamp works in code. We show a common struct with data and the timestamp. The struct is common in ROS. We show a code for a typical timestamp module. First, it reads the sensor data. Next, it reads the timestamp. Then the timestamp data is consumed by other control software. If we inject an interrupt in between get sensor data and get timestamp, say for 1 second, then the timestamp will be incorrect for robotic vehicles. Practically, we can use tools like SGX step for this purpose. This interrupt does not violate any SGX protections or policies. So why does the timestamp integrity matter? Let's see an example. We use obstacle localization in autonomous vehicles as an example. The goal is to find the obstacle localization in reference to the ground XP. We are given the location of the vehicle to the ground in particular time. We can see the path of vehicle as shown here. We are also given the LiDAR, which measures the locations of the obstacles corresponding to the vehicle at time TP. But the issue is the sensors are sampled at different time, so we have to use the timestamp to interpolate the position of the vehicle at time TP. We get the location of the obstacle XP using this equation. We see XP is a function of TP, so its derivative, delta XP, is also a function of delta TP, which is the timestamp errors. Thus, an interrupt will cause timestamp errors, which will lead to the localization errors. Let's see the impact of localization errors in experiments. We show the impact of obstacle localization error for robotic vehicles. Since the vehicle runs a collision avoidance module, wrong localization of obstacles lead to the wrong path of the vehicle, which we show here. The orange line is the straight path without an interrupt, while the blue line shows the path with the interrupt. We see an obvious deviation. We also show the average and the maximum deviation as a function of interrupt latency. In general, it increases with the interrupt latency, and the maximum deviation can be 0.6 meters. We also show Ego Localization errors, that is, locations of the robotic vehicle itself, not the surrounding obstacles. The input are odometry and LiDAR. It uses AMCL algorithm. The blue line is the ground truth locations, while the orange line is the location results where there's an interrupt. We also show the measurement localization errors and the relationship with the interrupt latency. The localization error increases with the interrupt latency. So for future work, we plan to integrate SGX-based timestamp module on autonomous driving platform like Baidu Apollo and evaluate the impact. We also plan to evaluate the recent research TE with interrupt protection for robotic vehicles, such as the following two recent papers. That's the end of the presentation. Thanks for attention.